Have you ever felt like you and your database are speaking two completely different languages? You ask what seems like a simple question and you get, well, something that's definitely not the answer you were looking for. What if we could change that? What if you could actually have a conversation with your data? Today, we're going to break down a new way to do just that. And trust me, it's a whole lot smarter than you might think.
Okay, let's start with a question that sounds pretty straightforward, right? How many chemical compounds are carcinogenic? You and I get it instantly, but for a computer trying to query a database, this is a total minefield. What exactly is a chemical compound in its tables? Where does it even look for the word carcinogenic? This is the exact kind of problem we're going to solve. And right here, this is the fundamental disconnect. On the left, you've got your nice, clean human question. And on the right, that's the reality of the database schema. It's this incredibly complex web of tables and columns and relationships. The whole goal of what's called schema linking is to build a bridge across that gap, to connect your simple sentence to that complex blueprint in a way that actually works.
So here's our game plan. First, we'll dig into why schema linking is such a tough nut to crack. Then, we'll look at the first part of the solution, making the user's question itself a lot smarter. After that, we unleash a really cool two-path strategy to find the data, and we'll walk through both Path 1 and Path 2. And finally, we'll see how it all comes together to create the perfect schema. All right, let's really define the problem here. There is this massive gap between the perfect, laser-focused answer you want and what a system often gives you when it's staring at a giant, messy database. We're going to look at why that gap is there and, more importantly, how we can start to close it. At the absolute core of this is a process called schema linking. You can think of it as the most critical first step. It's all about the system figuring out, okay, out of all these hundreds of tables and thousands of columns, which specific ones do I need to answer this person's question? If you get this step wrong, everything that comes after is pretty much useless.
And this slide just lays it out perfectly. If you just throw the entire database schema at an AI, it gets totally lost in the noise. It includes irrelevant stuff, it hallucinates, and the performance is, well, it's bad. That's our lower bound. But, and this is the key, if you could magically give it the perfect schema with only the exact tables and columns it needs, the accuracy skyrockets. That's the ideal, the upper bound. The whole challenge is figuring out how to get close to that perfect schema automatically.
So how do we start closing that gap? Well, and this is what's so interesting, the first move isn't to look at the database at all. It's to look back at the question we asked. The idea is that if we can make the question smarter first, the search for the answer becomes way, way more effective. So, to make this all concrete, we're going to follow one specific question through this whole journey. The question is, does bond ID TR001_1_8 have both element of chlorine and carbon? Keep this one in mind because we're going to see how it gets transformed. So this is how the question gets its upgrade. First, a large language model breaks down our one complex question into several smaller, simpler sub-questions. At the same time, it pulls out all the critical keywords and values, things like bond ID, chlorine, carbon, that are going to act like breadcrumbs leading to the right data. And here you can see the actual output. It's no longer just a sentence, it's a structured plan. The AI has broken it down into logical checks, and just as importantly, it's created this clean list of keywords. We've basically turned a fuzzy question into a sharp, precise tool for our search. Okay, now we get to the really clever part of this whole thing. Instead of just one straightforward search, this method uses something called bidirectional retrieval. It's like sending two detectives to solve the same case, but they each start from a completely different angle. I love this analogy. Think about two librarians trying to find a book. The first one thinks, okay, this sounds like a chemistry book, and walks straight to the chemistry section. That's our big picture, table-first approach. The second librarian goes to the card catalog and looks up the keyword chlorine. That's the detail-oriented, column-first approach. Both are really smart ways to get to the same answer. So let's follow that first librarian. Path 1 is table-first retrieval. This strategy starts from that 30,000-foot view, trying to figure out the most likely database tables before worrying about the tiny details inside them. And it's a pretty logical two-step process. First, the AI uses our newly augmented question to filter the whole database down to just a handful of probable tables. Then, and only then, does it look inside just those tables to pick out the specific columns we're going to need.
And for our example question, here's what path 1 came up with. It decided the most relevant tables were atom, bond, and another one called connected, and it pulled out these specific columns from each. So this is the first detective's report, if you will. All right, now let's check in with our second librarian, or detective. Path 2 does the complete opposite. It's called column-first retrieval, and it starts by hunting for those specific little details across the entire database. This approach totally flips the script. First, the AI scans every single column in the entire database, looking for matches to our keywords, like element or bond ID. Once it has a good list of relevant columns, it then works backward to figure out which tables those columns actually live in. And this is where it gets really cool. The result is different. The column-first path found the atom and bond tables, sure, but look, it also found this molecule ID column that path 1 totally missed. On the flip side, it completely missed the connected table. This is the perfect illustration of why having two different perspectives is so powerful. Each one catches things the other might miss.
Okay, so now we have two different results, but they're both really valuable and complementary. The last and maybe most important step is to merge them together into one final unified schema that really does give us the best of both worlds.
So how does this merge actually work? It's pretty smart. It basically takes a list of all the tables found by either path 1 or path 2 and puts them all together. Then, for each of those tables, it gathers up all the columns that either path identified. The goal is to maximize what we call recall, to make sure we haven't missed anything important.
And this is the payoff. Those two independent paths, each with its own findings, converge into this one final, beautifully compact and relevant schema. This is the perfect schema we were talking about at the beginning. And now that we have it, we are ready to generate a seriously accurate SQL query. So after all that, what does this actually achieve? What's the bottom line? Remember that huge performance gap between using the full, messy schema and a perfect one? Well, this bidirectional method cuts that gap in half. That is a 50% jump in accuracy just by being smarter about how we find the data. That is a game changer. So let's wrap up with the big takeaways. First, this proves that schema linking isn't just some minor detail. It's a crucial step that deserves its own focus. Second, this two-path approach finds that perfect balance. It finds everything you need, your high recall, without pulling in a bunch of junk. And maybe best of all, it improves accuracy right at the start, so you don't need complicated, messy correction steps later on. Plus, the whole framework is flexible and adaptable to different AI models. And that leaves us with one final big question to think about. This approach shows a massive leap forward in AI's ability to understand the rigid, structured, logical language of databases. So if it can get this good at mastering that kind of complexity, what other complex languages, what other systems is it going to master next?